In this video, we shall look at waves and some concepts associated with it. Assume we have a string, such as the one shown here, and we start to oscillate this string up and down, namely moving the string up and down in the direction of the arrow. You will see that you will form a wave, a sinusoidal wave, as shown in the figure. So as long as you maintain the movement of your hands up and down, you will see this waveform formed along the string. The direction of a wave propagation in this case is in that direction, namely to the right. So as such a wave pulse travels along the string, each segment of the string, say there, that is disturbed moves in a direction perpendicular to the wave motion. So that's going to move like that. A traveling wave in which the particles of the disturbed medium, in this case the string itself, move in a direction perpendicular to the wave velocity, that is the direction of the wave velocity. So such a wave is called the transverse wave. Now we shall introduce some important parameters associated with wave. Let's assume the wave moves along the x-axis and the disturbance of the string is along the y-axis. That distance there is called the amplitude, A. A is the amplitude of the wave. It is measured, of course, in the unit of meters, and that represents the magnitude of the maximum displacement of the elements of the string from their equilibrium position as the wave passes through them. The equilibrium position is represented by that x-axis. The second parameter is the wavelength that we can write with the letter lambda. It represents the distance between repetitions of the shape of the wave. So in this case, it is the distance from here all the way to there. So that distance right there is known as the wavelength. Next, we have frequency measured in the unit of hertz. It represents the number of oscillations per unit time. Frequency is related to period in a following manner. It is inverse of period, or period is the inverse of frequency. And period is measured in the unit of seconds. And we define period of oscillation, capital T, of a wave to be the time any string element takes to move through one full oscillation. So vertically like that. Up, down, up. So the time it takes to do that is the period of the oscillation. The next parameter is related closely to the wavelength. It is called the wave number, and it's denoted with the letter K. It is equivalent to 2 pi over wavelength. So since the wavelength has a unit of meter, the angular wave number or wave number has a unit of per meter. And finally, the angular frequency, which is related to the frequency in hertz in a following manner. It's 2 pi f, and the unit for angular frequency is radian per second. Using all these parameters, we can write a mathematical form for such a waveform. And it looks something like this. Since y, the displacement, the vertical displacement of the string, is dependent both on x and time, since this is a moving wave, it can be written using a sinusoidal function such as sine or cosine function. So the first term is amplitude times sine kx plus or minus omega t plus some initial phase phi. Note there is a plus minus sign, so which sign do we choose? If the direction of that wave propagation is to the right, namely along the positive x-axis, then we should choose the negative sign. If the direction of propagation of wave is to the left, namely along the negative x-axis, then we choose the positive sign. To better understand this, let's look at the following simple example. If you have a graph, let's say y equals to x squared graph. And if you have a second graph, and the graph look like this, it's as if this graph has traveled. Let's say this is x-axis, 1 unit to the right. What is the equation of the second graph? The equation is y equals to x minus 1 squared. Do you see the connection between the sign minus and the direction of propagation of that signal, in this case the parabolic signal? Likewise, if you have such a graph, and this point here is minus 1, then we write the equation for this graph as x plus 1 squared. Again, you can see the connection between the positive sign and the direction of movement of this graph to the left. So that is the mathematical basis that we use to choose the right sign when writing a waveform of a moving wave. What about this phase constant phi? That depends on the initial shape of that wave. Let's say the initial shape of the wave is a sine wave. Then in this case, the phase constant is quite simply 0 degrees or 0 radian. If the form of the initial wave is like that, namely a cosine wave, then phi is pi over 2 radiant, and so on. Of course, it could be anything other than 0 or pi over 2 radian, so its numerical value is dependent on the initial shape of the waveform. Problem 1. A transverse sinusoidal wave is moving along a string in the positive x-axis direction. The speed of wave propagation is 100 meters per second. At t equals to 0, the string particle at x equals to 0 has a transverse displacement of 5 cm from its equilibrium position, and it's not moving. The maximum transverse speed of the string particle at x equals to 0 is 20 meters per second. Find the frequency of the wave. So let's do part A. We were told that at t equals to 0, the string particle at x equals to 0 has a transverse displacement of 5 cm from its equilibrium position. Now that means the waveform has the following shape. So this suggests to us we are dealing with a cosine function. So let's write the transverse displacement of that string in a following manner. A is the amplitude, and we know A is 5 cm, namely the transverse displacement from its equilibrium at x equals to 0 and t equals to 0. Cosine, the wave number is k, x. Now it's moving along the positive x-axis direction, so we should use the negative sign, omega t, and that's it. Next, we know the maximum transverse speed of the string particle. Now this is not the speed of the wave, but the speed of the string particle, the maximum of it, is 20 meters per second. Now how do we get that? It is just the partial derivative of y with respect to time, and that's going to give us minus omega 5. When you differentiate cosine, you get minus sine kx minus omega t. Now we know the maximum transverse speed is 20 meters per second, so the term in front of that sign represents that maximum transverse speed. However, you have to be careful that this 5 is in the unit of centimeters, so we have to turn that into meter. So that is 5 times 10 to the power minus 2 meter times omega is 20 meters per second. That means your angular frequency is 400 radian per second. If we are interested in the frequency in the units of hertz, that's going to be omega over 2 pi. So that means 400 over 2 pi in the unit of hertz is the frequency that we seek. And the answer is about 64 hertz. So that's the answer for part A. Let's look at part B. What is the wavelength of the wave? Now we can use the fact that frequency times wavelength is the speed of propagation. So the wavelength is the speed of propagation, which we know to be 100 over frequency in hertz, which we have computed in part A, 64 hertz, and that's going to give you 1.56 meters. Part C, how do you mathematically represent the wave in that sine function form? We already know that the waveform can be described using a cosine function, and we know the amplitude is 5 in the unit of cm, so sine. K can be computed because we know the wavelength. We know the sign to choose is the minus sign because the direction of the moving wave is along the positive x-axis. Omega we know, t, and since it was a cosine function, the phase constant is pi over 2. Omega was found to be 400 radian per second. Now all we have to do is to determine the wave number. The wave number is given by 2 pi over wavelength. So 2 pi over 1.56 per meter. And that's going to give you 4.03 per meter. And we can write that in front of x. So the full function for the waveform is y equals to 5 cm times sine, the argument of which is 4.03x minus 400t plus pi over 2. Of course, you can write the amplitude in SI units, namely in meter, and it will become 0.05. And that is the final answer. Problem 2. A sinusoidal wave of frequency 400 Hz at a speed of 300 meters per second. How far apart are 2 points that differ in phase by pi over 4 radiant? So let's do that first. Let's first calculate the wavelength of this wave. Frequency times wavelength is the speed of propagation. The frequency is 400, wavelength is lambda, speed of propagation is 300. So that means the wavelength is 3 over 4 meter. The phase is given by the argument of sine or cosine. So that is the term kx minus omega t that we saw in the expression for the y. Now since k is 2 pi over lambda x and omega is 2 pi f, we can write the phase in terms of wavelength and frequency in a following manner. So part A asks you to compute how far apart are 2 points that differ in phase by pi over 4. So how far apart in space? So that means if the phase difference is pi over 4, we have to equate that to 2 pi over lambda times x, because we are interested in how far apart are those 2 points in space at the same time. Well, to be more accurate, we should write delta x instead to denote the separation distance of the 2 points. So pi get cancelled and you can determine delta x, where delta x becomes lambda over 8 in a unit of meter. Now we know lambda is 3 over 4, so 0.75 meter over 8 meter, which will give you 0.094 meter or 9.4 centimeters. Part B. What is the phase difference between 2 displacements at a certain point at times 2 milliseconds apart? So again, it's given by this complete expression at a certain point. So the point is the same, so you won't have the first term. Omega delta t equals that phase difference that we are interested in calculating. Omega is 2 pi f delta t. So 2 pi f is 400 Hertz, and delta t is 2 milliseconds, so 2 times 10 to the power minus 3 seconds. And the answer is 5.03 radians. Remember, we are calculating the phase difference, so the answer is expressed in the unit of radians. And that solves the problem. Thank you for watching.